we've been talking about linear regression, and we defined what we mean by Gaussian linear regression. It's this probabilistic model. We model these conditional distributions with a Gaussian or normal distribution, where the mean is a linear function of w, and in this case, since we can always specialize to from the general case of phi of x to this case where it's just linear in x. And now, but there's something sort of missing here, right? We wanted to come up with a function, go back way up to the beginning here. So we're doing regression. This was our setup. We have our data. Okay, we have assumed some probabilistic model. Linear regression says take this particular model, and it's natural, right? We talked about why linear regression is a very natural model to choose. But we need to choose some function f, and we haven't said what f we should choose in linear regression, Gaussian linear regression. So here's how you choose f. So we were motivating this by choosing, first we choose a discriminative approach, and that's a natural thing to do. We choose a Gaussian distribution for these conditionals, and then we chose a linear, so our third choice was a linear function here. So that was, so we could number these. This was our first choice, this was our second choice, this was our third choice. We chose linear and constant here, so very simple. And now, how do we choose f? So, how to choose f, and f is our prediction, our function that we're going to use to predict. Well, if we are thinking from a decision theoretic point of view, we should always predict, we should always choose a procedure, a decision to minimize our expected loss. That's what decision theory says. Minimize your expected loss. So, okay, well, we have a probability distribution, but what's the loss? Let's choose now. So this is our fourth choice. Our fourth choice is we'll choose the square loss. And this is the most, in some sense, the most natural, since we're doing a regression, right? So the y's are real valued, and we talked about why square loss is a nice natural choice in that case. So remember, square loss is just, it's this function L, and it's the square of the difference between your prediction and the true value of y. That's the square loss. And what is the square loss? How do we get f from the square loss? Well, let's see here. Let's make some more space. So, minimizing the expected loss, we're going to take the argmin over y's. Do you think? Remember back to decision theory stuff, of the loss of y is now random. This is the true y, and this is going to be our prediction. So we're minimizing over our predicted value, and we're conditioning on a particular value of x. So, okay, so I'm using a random x here, but we haven't introduced any distribution on these x's, right? The only random stuff was, this epsilon here. Or, the y's were random, but the x's were not. But it turns out it doesn't really matter, because, if you remember when we talked about, how to choose f using this approach, it didn't matter what the marginal distribution on x was. It only mattered what the conditional distribution was. And so since we're conditioning on x, then you can choose, take any distribution for x. It doesn't matter. All this works just exactly the same. So we have this conditional expectation, and our probabilistic model here for linear regression, it depends on this parameter theta, right? So let's assume some value of theta. So here I just mean computing the expected value of y, where we're assuming some w and sigma squared. So y is this thing, and theta is just like before. Theta is this. Okay, so let me just say that. So we're assuming some theta. Assume. So we want to solve this minimization, and when we looked at square loss, we found that you have the beautiful result that the argmin, there's a unique minimizer, and it's equal to just the conditional expectation of y given that x takes this value. So you can look at the video on square loss if you're not familiar with that. And now let's plug in what y is. So y is this thing, right? Theta is w and sigma squared. So y is this under this model. The inner product of w with x, the dot product, plus this epsilon, given x equals little x. And by the linearity of expectation, this becomes the expectation of the sum. This is a constant. There's nothing random here. All the randomness is here. So the expectation of a constant is the constant. And we get the expectation of epsilon, given x equals little x. But epsilon, well, I didn't exactly say, but usually unless you specify some dependence for a random variable, you always mean that it's independent of everything else. So epsilon here is independent of, well, there's nothing else random going on, I guess, at all. So epsilon, this expectation is just the expectation of epsilon. It doesn't depend on x at all. Oh well, I guess there is some other randomness. We're saying x is random here. So yeah, to be precise, we have some distribution on x, but we're assuming, so this is by assumption, epsilon is independent of x. And that implies, because when when you have independence, then you have this property for your conditional distributions. That's just a side note to remember why this is true. That equals the expected value of epsilon. If you wrote out the definition of conditional expectation, it's the sum of the values epsilon times these conditional probabilities, and you apply this, and then you just see that it's just this expectation. So this equals this, and this is just 0, right? Epsilon is a normal random variable with mean 0. So it's just the dot product of w with x. That is our solution to this minimization. And so we should choose. So our strategy, this tells us our strategy for Gaussian, to be precise, linear regression. I'm summarizing all of our assumptions here. For Gaussian linear regression with square loss, this is just summarizing our assumptions. We're doing a discriminative model. We're choosing a Gaussian conditional distributions, and we're going to use a linear. So all of these assumptions are coming together. The linear function for the mean and the square loss for our loss function. And the strategy is, how do we choose f? Well, we choose f of x to be just equal to the dot product of w with x. Super simple. So all that work looking at decision theory and all that paid off nicely here, so we can get this nice little result. And this minimizes your expected loss under this model. So that's a very, very, very nice result. It's unusual that you can really get the solution like that, and that it's so simple. It's just this linear function of x. Oh, how beautiful! Okay, so that's very satisfying. So this says, so we've solved the, well, so in some sense, we've almost, I guess, solved it. We wanted to choose some f to predict new y. So given a new x, then we'll predict a y using this very simple dot product way back down here. Okay, so there it is, using this. But wait, there's still an issue. So we want to choose this, but what's w? We don't know what w is. Okay. How are we going to figure out what w we should use? So, but we don't know. Now, this was, we assumed that we knew the true theta. This analysis here, this minimized the expected loss when y was actually distributed according to this theta that we assumed. But in general, I mean, basically all the time, we never know what the true theta is. So we don't know theta. We don't know the true theta. We don't know the true w. And that's where estimation techniques come in. I mentioned before that when we were talking about here, blah blah blah, discriminative, estimate theta using d. So we still need to estimate theta. This step still needs to be done. And we can use, so we have one final choice here. Our fifth choice would be, how are we going to estimate theta? And one way, at least, there's a few different ways, but one way, and perhaps the most natural way, would be estimate theta. Actually, we just need w if we're just doing predictions. But if we wanted to get this distribution, it's nice to have sigma squared also. So our fifth choice is estimate theta using the maximum likelihood estimate. There's different ones you could do. That's not necessarily part of the linear regression, but this is sort of the most common thing to do to estimate theta. And so now it's all the pieces are coming together. We've got decision theory, we've got maximum likelihood estimation, we've got supervised, we've got discriminative and generative. So all these pieces are coming together. And so next we're going to look at how you use maximum, what the maximum likelihood estimate for theta is.